I'm Dierickx. I'm a graduate student at Harvard CFA. And today I'll be presenting some of the work that I've been doing with Avi Loeb and Laura Blecka on modeling the orbits of local group satellites. And my title ended up being a little bit different from what's on the schedule because things changed. And I hope that's okay. So I'll start with an overview of what I'm going to cover in this talk. There's a lot that we can learn from dwarfs in the local group with quenching of low-mass galaxies like we heard about yesterday, to minor mergers, mechanics of accretion, and even the shape of the Milky Way potential, for example. And so one key aspect underlying all these things is having accurate orbital histories for these objects. So I'll talk about various approaches to reconstructing these, and then move on to presenting some of the results when we apply this to the case of M32 and the Sagittarius dwarf. So how do we infer the orbits of local group dwarfs? One approach is to compare their properties with analogs in large-scale simulations or surveys like SDSS or Illustris, and I've provided a couple of references there, and we've definitely heard a lot more examples of this already in this conference. But if you're interested specifically in one object and what its influence might have been in the local group, that's not directly helpful. And the method of choice there is direct backwards integration. And all that is integrating the equations of motion backward in time by introducing some minus signs. But in most cases, that's not actually an option. It turns out that proper motions are extremely difficult to measure. And even in a lot of other cases, there's non-time reversible effects at work. For example, tidal stripping operating over many passages near the host. And so I'll illustrate that with M32 first. This is the disk of Andromeda in the infrared. M32 is this tiny little blob here. It's not very impressive, but it's very interesting. Its proper motion is completely unknown. That of Andromeda actually has some constraints associated with it, but still, you're missing phase-space coordinates, and you can't do backwards orbital integration. So what can you do instead? Our approach was to bring in additional information and explore the parameter space of possibilities. What do I mean by that? If you look at the disk of Andromeda, you can't help but notice these really prominent rings of, at radius of about 10 kiloparsecs. And there's arguably some rings here, and on the outer edges too. And they're believed to be the result of a collision. Think rock falling into a pond, and you get the picture. And the prime candidate for that is M32. So what we did was to use a multi-step approach to testing possible trajectories for M32. Basically asking, under what circumstances does M32 produce the kind of rings that we see in Andromeda? And step one is to explore the parameter space fast with a lot of analytic orbital integrations. And then follow that up by looking at the best fit orbits with full n-body hydro simulations to see the effects that the interactions have had on the structure of both galaxies. So that's what we did for M32 last year in a paper that was published in 2014. And so this is a movie of the interaction and the stars and the gas. And there's M32 falling in. It has an impact parameter of about 10 kiloparsecs. And then it reaches its current position. I'm just going to let that loop around one more time. And in this simulation, the collision happened 800 million years ago, roughly. So with this collision, we actually reproduced the gas morphology of Andromeda. That was one of the main goals of the project. But what's interesting is that we do it for a off-center impact. I said 10 kiloparsecs, and high inclination impact as well. And that actually goes against previous works. For example, Bloch et al. 2006, which modeled polar head-on encounters, and we show that it's possible to do it with a wider diversity of orbits. There's more details in the paper if you're interested in that. Another highlight of this work is that the collision actually displaces Andromeda by 20 kiloparsecs, and that you may not realize translates to yes, it translates to half a degree on the sky at the distance of Andromeda, and that's about the size of the full moon, so it's a big displacement. And really, M32 has kicked Andromeda around in the past and has imparted it with a velocity vector. And that should be taken into account if you're interested in the dynamics of Andromeda, the streams around M31, like the giant southern stream, and so on. And one final implication of this work was we looked into the formation channels of M32-like galaxies. M32 is the prototype object of a very rare class of galaxies called compact ellipticals. And they're called compact ellipticals because they have extremely small half-light radii on the order of a few hundreds of parsecs. And they're very dense. They have very high central surface brightness. And we found that in M32's case, tidal stripping is not nearly strong enough to reach those kinds of half-light radii. Like this, the dotted line it's the half-light radii of M32, and tidal stripping never reaches inside of 2 kiloparsecs. So that suggests that at least some compact ellipticals are not the result of tidal stripping, and that they might start off as intrinsically compact objects before they interact with any host galaxies. Okay, now I'll shift gears with a few of our results on Sagittarius. So we applied the same approach that I described earlier for Sagittarius, and that's a significant improvement on existing studies that tend to either use ad hoc initial conditions, like we heard in Sukanya's talk on Monday, for example, or don't make use of the latest proper motion estimates. And so if we, for example, vary the mass of the progenitor of Sagittarius, going up in mass along this axis here, and then we also vary the initial velocity magnitude and velocity angle, and then we try to quantify the match to observed constraints like Sagittarius position and velocity, we actually get some pretty nice constraints on what the value of these parameters must have been at the beginning of the infall 5 billion years ago. So specifically, if we actually look at the lower panel, the 10 to the 10 solar mass progenitor, and we look at those blue lines, which are contours of constant angular momentum, we really do pick out one value of the angular momentum. And that suggests that we now have a really good constraint on what the angular momentum of Sagittarius was 5 billion years ago prior to infall. So if we run with that and take the best fit orbit and simulate it with Gadget, we can actually make a comparison to stars in the Sagittarius stream. So what I'm showing here is data from the 2 mass M giants in black squares, and also simulated stars in our stream as colored points. And these are color-coded according to distance squared, with larger distances, for example, here, as lighter shaded points. And I'm doing that just to give an idea of how far the stream ranges and what that implies about the detectability of those stars compared to what's actually detected in the data. And we have 3 panels, just the location, equatorial coordinates, the line of sight velocity, and the heliocentric distance. And this preliminary plot, this is work in progress still, suggests that at least our match to the data is pretty good. And that gives us some confidence that our model of the Sagittarius infall is not too crazy, at least. And we plan to do some more stringent comparisons going forward to quantify this better. So these are the take-home messages from this talk. Missing information and other challenges call for more sophisticated models of interactions in local group. We built such a model for M32, and as it turns out, M32 was probably very important in shaping the morphology and kinematics of Andromeda. We're currently carrying out a similar analysis for Sagittarius with results on the way, and we expect a lot further progress in the near future with more proper motion measurements coming out from HST, Gaia, and very large baseline interferometry as well. Thank you.
also going to cause something interesting?
What's, I think, important to keep in mind for Andromeda is that if the giant stone stream was on this plot for scale, it would be like all the way here. So I think the impactor, which is non-identified, it doesn't correspond to any of the satellites that we know around Andromeda, would have to be probably more massive and on a different kind of orbit than this. I haven't actually looked at it in detail, though.
Any other questions? David?
Yes, I was curious about your conclusion that perhaps M32 was very compact to begin with. Mm-hmm. What did you assume for the structure of the satellite in your modeling? Did you have some core component? Did you have a Sersic index? Did you have it round? I mean, just curious what you started with.
Yeah, that's a good question. And we actually tried many different things because basically one of the leading theories for how these compact ellipticals form is that they're the bulge left over after the disk and everything else has been stripped off of a bulge plus disk dwarf. So we tried that, and the disk stayed. It didn't disappear. And at the end of the day, the only thing that we found worked was to have a very compact sort of spheroid for the stars and then a pretty lightweight dark matter halo around that.
Sandy.
Does M32 have a tidal plume?
No. There's not even a clear sign of a tidal radius. So it's hard because it's kind of superimposed on the disk of M31. So when you're looking at the stars, you're always trying to decide whether they're an M31 or M32. But there's no clear boundary, and there's no tidal features.
Because within the ARC catalog, we're having a tidal plume.
Well, I might be wrong, but I would be curious to look at that up.
I'm pretty sure M32 does have elongation of its isophotes beyond, I think it's beyond 2.5 arc minutes. So this is the work, this goes back to work by Steve Kent. Phil Choi did this for his thesis. You can see clear elongation of the isophotes beyond a certain radius.
Okay.
Not so much twisting of the isophotes, but just elongation. In NGC 205, there's a very clear S shape.
Right.
There's very clear change in PA. But in M32, there's a very clear change in the ellipticity of the isophote at a certain radius. And it seems to be symmetric in that the isophotes remain elliptical, but and centered on M32. But as you say, it's very hard to make this measurement because it's sitting against this complicated disk of M31. So it's easier to do this at the longer wavelengths where the M31 light is relatively smooth. Yeah.
Okay. Yeah, M33 and GC205, it's pretty dramatic, but M32 is a lot, yeah, it's interesting.
Okay, I guess it's